Hi, I'm Ino Tereska. I'm a principal engineer in AWS, and I'm really excited today to talk to you about architecting for high availability on Amazon S3. Now, Amazon S3 has been running for over 13 years, and at this point has scaled to trillions of objects. In the process, we've had to scale the hardware infrastructure while constantly deploying software for things like fixes, updates, and new features. And we've had to do all of that while maintaining the high availability that customers require from S3. Now, we already know that S3 is durable. It stores your data safely and makes sure that the data is not corrupted. In this talk, I want to show that S3 is highly available as well. Practically, availability really means that a customer can access their data whenever they need to. Now, in this talk, I'd like to share some of the lessons learned during this past couple of years for architecting S3 for high availability, and I hope that some of those lessons will be useful for architecting your own applications for high availability. So let's get started. So this is the rough outline of the talk. I'll start by talking about the importance of measurements. Measuring availability in a multi-tenant service like S3 turns out to be super important, but also super challenging as well. I'll talk then about the end-to-end hardware infrastructure in S3, all the various components that make up the service, how these things can fail, and what we do internally to mitigate for those failures and maintain the high availability. Now, that's only going to be half of the story. The other half, it's really going to be about operational excellence and the culture of things like deploying software updates and also ensuring that we reduce the blast radius whenever something goes wrong. Again, that's also going to help in maintaining high availability. We're then going to put all these things together, and we're going to see how we can apply some of these lessons learned in S3 to your own applications through a series of case studies that show how we can design your own applications for high availability. Let's talk about measurements first. Now, measuring availability in a large multi-tenant service like S3 has bound to be challenging, right? There is a whole bunch of things going on in there. One of the challenges is that the risk is really having availability problems that really matter to a customer, kind of drowning in the noise of everything else that's going in the system. There's lots of other customers. You can have things like temporary failures or some network glitches. So the first question we're going to look at is what does availability really mean for a customer, and what do we do to measure it? Okay. Now, as we know, if you cannot measure something, you cannot fix it. Hence the importance on the measurement part. But before we talk about that, let's kind of go at a really high level, kind of 10,000 foot, and look a little bit at the components that make up Amazon S3. So here we have S3. It's deployed in many regions in the world. We have over 20 regions. We have over 60 availability zones. And inside these availability zones, we have things like data centers, facilities with power, cooling, lots of network switches, right, load balancers, and all that stuff. And all of these components, can fail in different ways, sometimes independent ways, sometimes correlated ways. Now, on top of this hardware infrastructure, we also continuously deploy software over all the microservices that make up S3, and there are a lot of them. There are over 100 microservices that make up the S3 service, and we're constantly deploying software onto it, right? Now, this is kind of like the messy reality, if you will, right? Now, the customers don't see this. Now, what do the customers see? Well, the customers see a nice kind of abstraction, buckets, objects, and they get the confidence that they can build on a highly available building block that S3 really is, right? So then the question really is, how did we get from that messy reality that we showed in the first slide, right, just with all those components, how did we get to such nice abstraction? And what did we do to preserve that availability? And what did we even do to measure that, right? So let's see what we do, right? So let's kind of come up with a couple of invariants for what it means to measure availability and kind of reveal them one at a time, right? So the first thing to note is, and this is really intuitive, is that availability is really personal to a customer. Okay, so if you're going to measure it, you really have to measure it per customer, right? We want to make sure we don't bias against more active users. So we want to make sure we have a good way to think about availability for a customer that's sending, say, 1,000 requests per second, and another customer that's just sending, say, 100 requests per second, or even one request per second, right? So that's the first bit. Now, what else do we need? Well, what's going to be the metric with which we measure availability? Well, again, intuitively, availability tends to matter whenever a customer is sending a request to S3, things like puts and gets and lists and delete, right? And if those succeed, then it's great. If those fail, then, well, we have an availability problem, right? So kind of naturally, the metric that we look at is things like request error rate. Now, is request error rate going to be sufficient? And there's a final part here which shows that request error rate is really not sufficient. So let's think about measuring this metric for an entire day. Things might really look good at the end of the day, right? You get a really good error rate and you might feel happy, but it might just be that during some intervals during the day when it mattered most to the customer, say during a 5-minute or a 10-minute interval, well, availability might have been not that great, right? So intuitively, again, what we want to do is measure this error rate, this metric per customer, but during a fine-grained time window or time interval, right? And that's really going to be this third part. And then once we have it on this window, then we can reason about the entire day. We can split it into these windows and these intervals and really have a good picture of what the user is experiencing in terms of availability. Now, what else do we need internally? So let me add a little bit of complexity here. So I've gone ahead and added a bunch of disks, which is one of the resources inside S3, obviously, where we store the data. And I've added a couple of more blocks here that we need to keep track of internally. So the first thing the next thing really that we need to measure when it comes to availability is things like, failure rates. How are devices, how are some of these components failing inside the system? Now, we don't want to wait for the customer to experience those failures. The way we measure them is that we have integration tests, canaries that are constantly running in the system, and they're reporting more than just averages. They're reporting entire distributions of this failure rate. So we get a really good picture of how things are failing. What's the next thing that we want to measure? Well, arguably this is one of the most important ones. It's really the repair rate. How fast, how quickly can we really go and restore if there is any problem? So in this example with the disks, maybe one of the disks has failed, right? So the data is not as redundant as we would like it to be. To maintain availability, I'll talk a little bit later about this, but we replicate the data, right? Really, we want to measure the repair rate. If something goes wrong, how quickly can we get back to a good state in the system? So all of these components, the measurement per customer, the error rate during an appropriate time interval, and things like failure rates and repair rates, all of these things go into what we call an availability model. And this availability model then is represented with the nines that you can see in some of the documentation. So this is the first part really about the measurement. Now, measurements are important, but let's have a little bit of a look into how do the various components inside S3 fail, because it's not sufficient to measure things. You also need to mitigate whenever there's a problem inside the system, right? So let's look a little bit at end-to-end robustness inside Amazon S3. Now, one of the quotes that we like to cite internally is that everything fails all the time, right? Now, this doesn't mean that everything is actually failing all the time. It just means that as software engineers, we need to think about failures all the time. We need to reason about how we're going to mitigate and resolve some of these failures whenever they happen, so we can maintain high availability in S3. Now, let's go back and look at that slide that I showed about S3 at the high level, right? So I talked about, it's in all those regions. We have availability zones. We have racks, switches, servers with resources like CPU, memory, disks, solid-state drives. All of them can fail either permanently, where they never come back up again, right? You have to replace them by something new, or they can also fail transiently. Something goes wrong for a little bit, but then everything becomes just better by itself, really. So let's take a kind of like a top-down view into what's happening here. Let's look at an entire facility first. Now, the goal here is going to be that to maintain the high availability, right, we want to tolerate facility failures, whole buildings failing. Now, this is a super rare event, by the way, but let's just talk about a couple of reasons why those buildings may fail. You might have power cuts, right? You might have flooding, you might have earthquakes, or any other hazards inside your system.
Now, intuitively, to tolerate more than one facility failing, well, you need more than one facility. Then you need more than one, right? So you can have a bit of redundancy in the system. We'll see this notion of redundancy coming up again and again in this talk. So S3 leverages something that AWS makes available for its customers called availability zones, right? So these are independent failure zones that we offer customers. Each of them might have one or more data centers. And these are all physical separate facilities, right, in one metropolitan area. Now, they have power redundancy, network redundancy, all of that in there. So we can think of that as independent failure domains. Now, we have the buildings, which is great. But how does S3 make use of those buildings? The second part really is how do you spread your data? How do you store the data across these buildings to ensure high availability? Well, all the storage classes in S3, with the exception of one of them, store the data across more than 3 availability zones. So even if one or two of them fails, the data is still available. The one class that stores it on one availability zone is the one zone storage class. And that kind of like exposes this trade-off to the customers that there will be sometimes data that doesn't require such high availability, and for that data you can have lower cost. But the bottom line is that S3, to tolerate some of these facility failures, it stores data across multiple such facilities, leveraging the notion of an availability zone. Now, just because we're replicating across availability zones doesn't mean we're all done, right? We also want any one of them in particular, any one of these facilities to still be reliable, to still be highly available. Now, hardware will fail inside those buildings despite our best efforts. So the goal really is to, one, protect the data, and two, make it available for the customers, even if hardware is failing inside the system. Typically, there is a low rate of component failures that we've observed over time. So over these years, we've collected information about how do servers fail, how do disks fail, what are some typical hardware defects, and also we make reasonable assumptions that are really based on what we have observed about how correlated are the failures inside the system, right? What are going to be the mechanisms? So that was really the goal. We want to tolerate these hardware failures. There's really 3 things I want to talk about, right? The first one is again redundancy, but at a smaller scale in this case, right? So have redundancy in everything. And here I'm bringing back this picture of the disks because it's a kind of an easy example, really, for disks and for your data within one of these facilities. What this will mean is that we're going to have multiple copies of the data, and therefore have some redundancy. So if any of the disks fails, the data is still there and available for the customer. Now, you can apply the concept of redundancy to power, to cooling. For example, these availability zones and facilities often are connected by more than 300 unique fiber paths that even if some of them fail, you still have connectivity between the buildings. The second part is really you want to improve failure detection. Okay? And the way you do that is by having good tests in place. Again, we don't want to wait for the customers to discover some of these problems. We want to be proactive. So good tests in place, good canaries there that proactively find if there is anything wrong with the infrastructure. They report it so that we can repair it quickly. Sometimes improving failure detection might also mean kind of being predictive, predicting ahead of time what fails. And the other thing that sometimes it means it's this subtle thing where oftentimes inside the software in S3 there are timeouts for how long do you wait until you declare something failed, right, like a disk. And we've tuned those timeouts so that to something that gives us good availability for the customers. The final thing, which is arguably the most important thing, is that we also want to continuously improve the recovery times. Recovery means that, in the disk example, if some of the disks have failed, if the data is not as redundant as it should be, for example, if you wanted 3 copies, but one of them is not there, you want to bring up the redundancy to what it was before, just in case you have any correlated failures, and you want to do that as quickly as possible. And for that, I'm showing here in the picture we have the concept of an elastic repair fleet, where we can adjust the elasticity depending on the kind and number of failures that we're seeing in the system, and speed up the process as much as it makes sense to improve the recovery and the repair times.
So that's what I wanted to talk about. So we talked about facility failures, and we talked also about the failures inside one particular facility. Now, there was this flavor there that we didn't kind of explicitly say, well, are these going to be permanent failures? Are these transient failures? Sometimes they are permanent, sometimes transient. Now, I just want to double down a little bit on this notion of a transient failure, because this will require a little bit more thinking here. So you might have a transient failure. Well, we in S3 might have a transient failure, really, if there are things like networks might be temporarily overloaded, switches might be dropping some packets just temporarily. And on your end, you might also notice things like the DNS is not resolving correctly. And then the question is, what are some of the mechanisms that we want to deal with these transient failures? And some of them are kind of small, but they kind of add up, right? You need to do all of them to kind of get the high availability you require. So, for example, one of the mechanisms is to propagate the right error code throughout your software layers. So, for example, if one component is busy temporarily, it's throttling your requests, it then sends the right error code, the 500 throttling error code, to the other layers, and it just tells them, look, I'm throttling you, just try again, right? And this way, the other layers know when to retry and know that really there isn't really a permanent failure. There is just something that is worth retrying. Now, when do you retry? The amount of jitter and exponential backoff, that's all tuned internally in S3. And very importantly, this is also made available to the customers for the rest of their code, for the rest of the client code, through the AWS SDK. So kind of like one high bit here I want to talk about is that it's really important whenever you have one of these problems to make sure, the first thing to do is to make sure that the AWS SDK is up to date. All our fixes go there, so if you get the latest update, you're bound to get some of the fixes and some of the lessons that we have learned in the service. You're bound to get them to your client code, right? Now, there's always going to be a little bit of other things you might need to do in your environment. So, for example, if the DNS failed to resolve, and sometimes that happens, we do change sometimes the DNS entries on our end to maintain high availability. If that fails to resolve on your end, you might have to check things like, if you're using Java, you might want to check Sans JDK, JVM, because oftentimes it's going to cache those DNS entries forever. Okay, and like a simple change there, changing the time to live in the cache, for example, to something like 60 seconds, it's going to make a big difference. You don't have to restart the JVM. You can pick up the DNS changes, and again, ensure that your applications see the high availability from S3. Good. So we talked about failures, hardware failures, and permanent and transient kind of failures. Are we done? Well, actually, we're not done yet at all. So there's going to be this super important part, the operational part. That's going to be, one lesson we've learned over the years, that this matters as much as all the other stuff we talked about, right? So one of these things that matters a lot is, how do you do software updates in the system? I mentioned S3 is a large system over, hundreds of microservices, and they're constantly updated. There is no like such thing as downtime or like a planned maintenance window or anything like that, right? So it turns out that the way you do those updates and the kind of like the operational culture around them would matter a lot. So let's have a look, right? So the first thing I want to talk about is the architecture for the updates. And if I have to pick one thing, I'd like to pick on reducing the blast radius if something goes wrong during your update, right? So for that, we use this notion of a cell-based architecture. What's a cell? Well, it's a cell is really like a set of devices kind of work together, that operate together, and they do useful work together. Once you update that set of devices, any new customer code that accesses them is going to see the new software that you have updated. So the way that we update software continuously is one cell at a time. It sounds really simple, right? But there are a couple of neat things there. So for example, automatically we have the right tools in place that every time we update a cell, the monitoring kicks in. Is it working well? Is the new software working well? If it's not working well, automatically it's rolled back. You don't want to debug and diagnose the problem. while the customer might be having an availability problem, right? We want to first roll back, diagnose the problem in our own time, and then move forward whenever we've fixed it. On the other hand, if the tools don't detect that there is any problem, we just go ahead and update all the cells one after the other. So the cell-based architecture is very important in reducing the blast radius whenever something could go wrong during the software updates. Now, the second part is really robustness in face of operators' mistakes. So I talked about how the first thing we use is automation, of course. So all this, rollbacks or all the scripts and the runbooks, the first thing we try to do is automate as much as possible. Sometimes there will be new features or other aspects of the system for which an operator does need to be involved, right? And humans make mistakes. We're not going to change that fact. What we want to do is to really ensure that those mistakes do not lead to periods of unavailability for the customer. So one of the things that we use for that is this notion of good tools that apply this principle of least privilege. So this is one of the things I'm kind of picking on. So for example, we ensure that operators have the right privilege to run the right tool for the task at hand, and really no more than that. And whenever they are not on call, they don't need those privileges again, right? So we're talking about tools, so let's kind of double click a bit on the tool part. So good tools are super important in maintaining the operational excellence in S3. And we do all we can to prioritize tool improvements. We review the tools the same way we review the code for the main features. Now, what are good tools? Like, good tools are things that do not require a necessary input that can be inferred, for example. And that way the operator doesn't have to type things, and therefore we reduce the number of mistakes that they might be making, right? Good tools also perform safety checks and fail safely. They don't leave the system in a bad state. So again, the idea here is to make, we don't want to avoid misuse because that is bound to happen. It's just we want to make the misuse safe and therefore maintain high availability in the system. Now, one more thing I want to talk about, and that's about this organizational structure that really encourages deep root cause analysis. So say something has gone wrong, say we have to discuss, a particular failure we didn't notice before. We all get together and in a non-judgmental way, look at a whole bunch of things. And I want to share a little bit the format of this meeting because it's really good, and I think you can use it for your own organization if you want. So in this meeting, we talk about what happened, what is the customer impact, and then we go into this series of 5 whys. Now, it doesn't have to be 5, it can be 3, it can be 10. But the bottom line is that we kind of drill deep in each of these layers. You might have had some, one layer like a disk might have failed, but the next layer above maybe didn't handle that failure correctly, right? And then the layer above that also, didn't do the right thing. So through these 5 whys, we really, drill deep inside the code. And then the outcome of the meeting is really simple. We have, what do we need to change? What are the action items? And who are the owners? And what are the dates? And then we prioritize this above anything else. Good. So we talked about the organizational structure around things like operations and software updates. And to start with, we also talked about the hardware failures and the lessons learned there. Now, let's put all of this together and see how can we apply some of these lessons for building your own application. So how can we build applications that are highly available? Now, if those applications have state and you're storing that state in S3, you don't need to do anything. So that's, you don't need to worry about the state, but you might need to worry about other parts of the application. For example, compute instances, right? And you might want to make them highly available. So let's look at these scenarios one by one. So the first one is a customer that has their own customers, right? That and this customer wants those customers to be served with no downtime, even if there is a failure in the compute instances, right? So again, like the high-level goal is that good reliability, good robustness in face of compute instance failures. Now, these failures can be transient or permanent, right? So going back to what we used inside S3, the main concept there we used was this notion of spread your data, in this case, spread your instances over multiple availability zones. And therefore, if one of them fails, you still have the other ones You can still be highly available. And indeed, this is one of the main mechanisms that this customer can use to maintain high availability. You can also use for compute instances in particular notions like AWS autoscaling, which with the automated health checks, and if there is a problem with the instances, it's going to bring up the right instances at the right availability zone. So that's the first thing you can use. Now, as I mentioned, if your data is stored in S3, you don't need to do anything. If the data is stored elsewhere, in addition to S3, one kind of recommendation there, if there is anything we've learned, is the importance of repairing and recovering the data as fast as possible. So if you can do one thing, would be try as hard as you can to recover the data. Now, in the second case study, we have a customer that wants their applications to continue to operate even in face of network failures, which is a simple ask in a sense, right? But we know the network failures are in this category of transient failures, right? And you might have something like DNS is not resolving, for example. What are the mechanisms going to be? What have we learned in S3? Well, one of the things we have learned is that many of the problems just result from the customer having an out-of-date copy of the AWS SDK. So the first advice there is make sure that the SDK is up to date, that you have the latest copy. All sorts of fixes are captured there in terms of retries and timeouts and all the good stuff, right? The second one, if you're having a DNS issue, and this is like super specific, right? Oftentimes, especially if you're using Java, Sans JVM might cache the DNS entries forever. And just to fix that, you might want to simply change some configuration parameters like the time to live and make it to something like less than 60 seconds, for example. And that way you can pick up new DNS entries all the time, and you won't have trouble re-resolving DNS. In the third case study, we have a customer that wants to deploy bug fixes more frequently, but they're worried that the more frequently they deploy those fixes, the more downtime there will be for their customers, and they really they would appreciate it if they could minimize the downtime. So what are some of the mechanisms we talked about? Well, the first thing is about the architecture, and we talked about this cell-based architecture where you deploy the software one cell at a time. You have automatic measurements in place that if they detect anything wrong with how the software is behaving, immediately roll back the software. And then you can diagnose it in your own time. If things go well, then you can proceed one cell at a time. So this cell-based architecture is going to reduce the blast radius. The other thing we talked about is tools and the principle of least privilege. So this customer might want to apply the principle and, for example, disallow SSH access to the instances of that application. And through that, in a sense, the operator will just have a reduced kind of surface area with which to work and just the right tool for the right task at hand. And therefore, through that, ideally, this operator is minimizing the kinds of mistakes they can also make with the system, and therefore maintains high availability. Good. So those are the case studies that I wanted to talk about. So in summary, we talked about the importance of measuring availability. If you can't measure it, you can't fix it. It's challenging. It's a multi-tenant service, but it can be done. You want to do it per customer at the right metric, at the right time granularity. Then we talked about end-to-end robustness in S3. We talked about some of the hardware components that make up S3 and how we mitigate errors and failures in those components, permanent or transient, to maintain high availability. That was just part of the story. In the other part, we talked about software updates. How do you do them to reduce the blast radius? How do you do them continuously? And we talked about the importance of an organizational culture that values operational excellence and deep root cause analysis. We took then all those lessons learned and applied them to 3 customer case studies. And we saw that customers can use these lessons learned to build their own applications for high availability. Thank you.